I'm very pleased and honored to be here. I feel a little bit like a rock star today. I hope with these expectations I'm actually able to satisfy them so that you can go home with some additional things that you might not have known about Google. So indeed, until 5 years ago, I was mainly an academic researcher, also an entrepreneur, started a company that is still flourishing. But 5 years ago, then I started to join Google as an engineering director, not so much a research role, but in a role of building things and improving actual systems at Google. And the Zurich site in these years has grown from 40 to about 800 software developers that we have on site. So that is also a sign of things that happen at very few companies, including companies like Google. So this will be a talk about Google, but it's not really a talk about just the company. I will talk about Google as into Google, that was already alluded to before, about things that happen at a large scale that you could call a Google scale, and then various other aspects that have to do with Google, but that are also more general. They also have to do with maybe the last 10 years of evolution on the web, some change that we're seeing in some industries where business model change, user behavior changes. It's just amazing. When I look back 12 years ago, for instance, I was first considering to join Google, but then I said, no, I just opted for the academic career path. It was very hard to predict what would happen, right? And we tend to forget the rapidness and the scale of change that we've been witnessing. So anyway, I will walk you through 7 episodes, if you like, about Google that I think reveal interesting things. So let's start with Google as into Google, or information for billions. And by the way, 2006 was when Google was officially added to the Oxford Dictionary. So at Google, you might have heard this, we have a mission. It's probably the first slide in every talk that someone from Google gives, which is to organize the world's information and make it universally accessible and useful. The thing is, though, that although it sounds like simple and somewhat, like a formulaic, it's actually something that over the 12 or 13 years of the company, we've actually used that principle and constantly apply it in our strive for bringing more information online, making it more useful. Everything from the Google Books project of scanning additional resources, Street View, and so on and so forth, can be summarized under that umbrella of Google's mission. Now, since we really work on a global scale, we have to think basically of everyone out there in the world as a potential user. Today, or end of March, I think we have these numbers. There's about 2 billion internet users in the world, almost half of them these days in Asia, which is growing, but really all around the world. And that is only like part of the users, because we have more and more users that use mobile phones, some of which and more of which are internet enabled. So there's even 5+ billion of potential users in the future that will be connected to the internet via mobile devices. And of course, the principle at Google is that we would like to build products that are simple and intuitive to use. You cannot train 6-7 billion people in the world in complicated ways how to use a product, right? When I was a student and I did search in the library, it took a librarian to sit down with me for an hour to really issue the right query and to find the books that were relevant. At the time I was still studying philosophy, maybe that's why. But anyway, right, things have changed. Today there's no librarian that sits next to you at home, right? But you just type in something you expect to get good answers. We're used to that. But although it's simple and intuitive on the surface level, of course the technology behind it is far from trivial, is far from simple. Most of you will know that. Why is search, and that is, I think, what most people associate with Google, so important? It is important because it is the dominant way of discovering information on the internet. So there's lots of statistics here, and that most people use search to find information. Of course, there's also other ways that you can discover information, and there's other search engines than Google. I would try to convince you, although I can only be at the surface level, that search in some sense is kind of a rocket science, although it doesn't look like it. So the engineering effort that goes into it requires a lot of innovation, and a lot of engineering limits have been pushed over the years, some at Google, some in other places. So if you think about the 10 years or so of web search evolution, what we have today, just in terms of scale, is about 1 trillion URLs out on the web that we would like to build an index upon, that we would like to make searchable. We have, that was in the title, around 1 billion searches per day at Google. And then, there's even more searches also for other search engines. And also another interesting fact is there's about 1 million spam pages created every hour. So while I speak today, when we leave the lecture room, there's 1 million more spam pages out there, trying to get indexed by Google to make it high up in the ranking. And that is also part of the work that we do, is try to preserve relevance and fight people who are exploiting search engines to basically promote their content and their business. Of course, if we go back to 2001, what was the key innovation at Google? Most of you have maybe heard of this. It's known as the PageRank algorithm by Larry Page and Sergey Brin, the two founders of the company, which is basically performing a Markovian random walk over the web page graph following the links. So you can imagine there's a random surfer that surfs around on the web, and then basically you do that for an infinite amount of time and compute the average time that surfer was spent on a particular page, and that would give you an authority score. And that authority score is an intrinsic score just derived from the web, the link structure, and that has helped at the time to really distinguish between kind of low authority or low quality content and high quality content. But that was only one key innovation that got the company started, and there were many more to follow, some of which I would like to talk about here. There's also one thing that at Google we had to get right. For those of you who have been using the internet in the early days, there were several attempts to monetize, through advertising mainly. You had pop-ups, you had like screens that you had to stare at for 30 seconds before you could actually do something and look at ads, right? And there were also attempts in the search engine space to basically just, promote certain search results. Oops. Not sure what I did here. Let's see. There were Microsoft and Google software. There are all these ifs, these weird if statements in the code. So maybe I shouldn't use that mouse. Yeah. So there were all kinds of attempts to monetize in the search context. For instance, Yahoo in the early days, and I think they still practice that, was basically to ask publishers, owners of that web content, to pay for making it up higher, to come higher up in the ranking. Sorry about that. And so basically, the problem with that was that you were never sure whether you were getting a result because it really deserved to be in that place based on its relevance versus whether it has been paid for. And in the Google context, it's also not the case that we wouldn't show advertising. That's basically part of the business model. I will come to that. But one philosophy is really to basically split the screen estate and to, educate users that over here there are ads, and then whenever you see this funny background color, these are ads, and then here you have your organic search results, right? So anyway, let's come to some of the innovations in search that we've been working on at Google. So, and one thing I need as a basis here is for you to understand, what are the core parts of a search engine. So one thing is that if you want to search over the web, you cannot do it when the user gives you the query by linearly now searching through all the web pages, right? So imagine, there's a couple of billion web pages, I download them all. I cannot now start searching for, let's say, the term Oxford, finding all the documents that contain the term Oxford. Basically, the idea is I do that beforehand. I create a data structure that's called an inverted file index, where for each term I store a sorted list of document IDs that contain the term and possibly other information like the position where that term occurs in the document. So you see here, for instance, if you have a name like Brutus, right, you would store a list that would contain numbers. Now, these are all very small numbers. In reality, right, this would be a much, much larger document ID space. And so it's a little bit like, at the back of your book, where, you look at a keyword and then you find the pages where that term was actually mentioned, right, only on the web scale. What we also do then is, if you think about this, these lists can become pretty large, right? Let's say there could be tens or hundreds of millions of web pages that contain the term Oxford. We partition this whole index based on doc ID. So we would be saying that we look at a particular machine that would be responsible maybe for the first million documents, and then another machine would be responsible for the second million, and so on and so forth. So if we have 1,000 machines, we can cover, let's say, 1 billion documents. Each one would be responsible for 1 million, and we would split the index. And so basically, each machine would contain part of the index restricted to that subset of documents. And this is then how, in a sketch, a typical search engine like the one we use at Google at a high level looks like. So you have a query, someone types Oxford into the search bar. It is sent to the front-end web server. That front-end web server fires off the query to the advertising system. I'll talk about that later. It'll look up in the cache servers whether that query has been issued by someone else recently. If so, it'll just get the result from the cache and no work needs to be done. The cache server basically stores historic results. And then if there's some actual work that needs to be done, it's sent to the index servers. Now, the index servers are sharded, as I said, right? So each shard would contain a part of the web. Let's say 1 million pages of the web would be indexed with each shard. But you would also have replicas, right? Because you now have lots of traffic, coming to these index servers, and it's not a good idea to just have like one machine, be the only one that has that specific shard, but you actually replicate it. And if the traffic grows, right, you just can then scale up your system by increasing the number of replicas. The front-end web server, or in fact, this will be a tree, where things will get routed will depend on what the current load is on this machine, right? A machine is very busy, and a new query comes, it will be sent maybe to another replica that is less busy, right? All these machines will do the index lookup and then propagate the results back up, where they will just be merged and then really ranked or sorted according to a score that is given to the document, and then the top 10 or so links are actually shown to the user. All of that needs to happen in, so here, 0.24 seconds. So typically 200 milliseconds, right, is the way we do this. And you can see that really what happens here is that on that side, for instance, right, there's only 200 milliseconds, but there are maybe 1,000 or more computers that do the work in parallel, right? So the total compute time is 1,000 times 200 milliseconds. But of course, since we don't do it just on a single computer, the latency is much, much better, right? Because we parallelize work. And that's actually this whole parallelization and divide and conquer principles are the most basic strategy, right, in getting things to work at scale. We also need the document charts where we actually keep the web pages themselves, and that's basically to produce things like snippets. So if you see the search results, we also show where the search term matched in the context of that web page. In order to do that, we cannot find that in the index. We basically need another system that then returns the snippets for these results. So, and that happens 10,000 times per second now, right? Every time of the day. The peak load is even more, like when people wake up in the US, it can easily be several 10,000. It can be in the hundreds thousands of searches per second. Right, so that is a lot, and we will come to later also what that means to really do that at that scale. But that's the principle of the architecture here. We're doing, of course, more things. So some of the innovations in recent years. So one thing is Google Suggest. You've probably experienced that. You start typing. So for instance, here OX. And we basically offer query suggestions, like Oxford being the #1 here, but also Oxfam, for instance. What we're basically doing is we're trying to predict the probability that you're trying to type a particular query given the prefix that you've already typed in the search box, right? And we give you the best results. This needs to be extremely fast, much faster than returning search results, because as you type, you want to see these things, right? So this is in the 10, 20, 30 milliseconds range where we need to deliver these things. So it creates a very heavy load, not to wait for your enter key, right, and to start starting inference about what you actually might be interested in. In order to do that, of course, what we do is we mine query logs at a massive scale. We look at what type of queries user issue, right? And then for each prefix, look at what are the likely completions. And needless to say, we need to filter out a lot of bad stuff because, you know, sometimes you don't want to know what people who start with a certain letter or prefix are most likely to ask for. At least you don't want Google to suggest that to you. So it's not just statistics and machine learning, it's also a lot about data curation and filtering and not showing inappropriate content. And whenever we show inappropriate content, of course, it'll probably be in the press tomorrow, so we need to be very good about really not making that happen. And then, of course, there is what we call Google Instant, which is not only it suggests the query, but actually, when you type OX, it already assumes, well, Oxford is actually quite likely, so why don't we just do the search while you try to type, you know, the third letter, we already give you the search results, right? So at Google, we are kind of impatient, right? You can see that, and so why wait for the enter, right, to be hit if we think we know what you want? Of course, sometimes that can be a bit confusing because maybe I didn't mean Oxford and then you show me already results for Oxford. But I think it's a pretty cool technology. Overall, in user studies, we've seen that it increases the speed at which people find results by maybe a few hundred milliseconds per search on average. But multiply that by 1 billion, so there's already a lot of time that people can spend on other things if we can save that. To do that, it's really not trivial. So if you imagine what happens here is that we have a much, much higher search load. So actually when we activated that, right, it's typically now 2 to 3 searches that we do per actual search because we already start searching and presenting results, but then the user might type something else, right? So that required a lot of back-end serving optimization, caching is important, and so on and so forth. So it was a huge thing to roll that out within the company, but it has shown that we can really do things that no one else can do at that scale. Oops, sorry. We also do things like real-time search. So while I was working on this presentation, there was a tennis match going on between Federer and Nadal in Paris. And you type Federer and already you get the results and you get real-time data being fed into this. So it's not always that we have to wait for something on the web to appear, but often we have our own real-time data sources with live results and that we can blend into the search. So that is also one innovation of the last year or two. Something we did that dates back maybe 3 years now, 2-3 years, that was also a major redesign, so that you understand another challenge, is illustrated in this picture here. What happened was we started with web search and then we added news and image search and blog search and video search, where people would actually go to the video.google.co.uk, right? And then they would search for videos. And then you would go to news and then you would search there. And we felt, well, that's kind of stupid because, first of all, people have to go to all these different, right, search boxes and type the same query, where really we should know what type of result to return. Is a web page good? Should we return news? Should it be a book? Should it be a video? Should it be an image? So basically what we did is we moved from this left-hand architecture. Well, that was the first thing of bringing it together, where we said, okay, we look at the query and now we decide, David Beckham, maybe web results would be good and images would be good. And there was a learning system that would try to classify the query correctly. But it's often very hard to know whether there is something in your backends, right, and making that decision beforehand. So what we did with Universal, what we call Universal Search, is basically send the query to all backends, right? So now that means every web query is sent to the news corpus, to the image corpus, to the video corpus, books corpus, and we're looking for results. that basically meant that all these systems that were currently maybe seeing, a percentage of the web traffic suddenly are exposed to 100% of the web traffic, and they needed to be scaled up, and they all needed to be upgraded in terms of their infrastructure because the traffic would increase 10 or 1,000-fold. It's another example of saying, starting with web search and the specialized search, saying that search should really become like the common entry point for all these corpora. They should all be together. A user shouldn't have to make that decision beforehand, but we should really do our best using all the corpora that we have. Then there's spam. Most people are, might experience that every now and then, but most of the spam is we try to keep out. But you should realize that the web search is really an arms race. There's huge economic incentives here. If you rank highly in Google for a popular query, you get a lot of user attention. User attention is money, right? That's kind of the attention economy, right? You can monetize it. So where there's huge economic incentives, there are always smart people. They might not be the most honest people, right? But there are certainly smart people who say, well, how can I take advantage of that? And I think that's all fine, but there, of course, is a threat that spam potentially could render web search ineffective, right? If we only see spam, then at some point we couldn't use a search engine, right? There was no way to really maintain a healthy search engine. So we are constantly fighting spam, and part of why everything related to how we rank things, the result ranking, why is it these 10 links in that order for that query? Some of the secrecy around this is really to avoid that things can be reversed engineers. Because, if we would just say, this is the formula we're using, everyone out there could try to optimize, right, their website to really make it up high in the ranking, and that might not be to the advantage of the user, right? But it is a huge problem, and there's lots of work that happens there that I cannot talk about, but I just use that slide as a placeholder. But I'd like to point out, like in general, how we work, because I think that is also interesting. It's not just how Google works, but it's how many companies work, Facebook, Yahoo, at Microsoft. And you should understand that it's interesting from an engineering perspective. So usually what happens is, right, you have smart people working for you. They have ideas, right? And the way we approach this at Google is we say, well, okay, take your idea. Okay, here's a sandbox, like a simplified environment where you can quickly, since this is software, right, you can basically build a prototype. You can code this up in this sandbox. And then what you do is you sample a few search queries. Let's say if we're optimizing web search, and you look at what you get with the current system and what you get with a system that you have presumably improved with your idea. And then you take that and we send that to raters. Okay, we tell raters in the simplest case, do you like this or that site better, right? Which results are better? And we do that with a sufficiently large sample size so that we can get statistical significance. And if we're happy with it, then we might actually go to live experimentation where we say, okay, maybe 0.1%, right? So every 1,000th query, 1 over 1,000 query, we send now to run your system, right? That includes your idea that modifies search results in some way, and the other 99.9% we just run with a standard system. And then we get lots of data, right? Because we have 1 billion queries per day, so even 1,000th of that is still 1 million. And then we can look at that, and then we have an independent analyst team that basically prepares a report, and then that report with a recommendation is brought to a launch committee. And then the launch committee can say, well, that's great, let's just do it and launch it. Or it could say, well, that needs to be improved. And then you're back to the drawing board and you enter that cycle again. Okay? That happens a lot. So here are kind of numbers. 2010, we had about 23,000 ideas that were tested through what we call precision evaluations. Around 11,000 that were tested side by side. So that is like a couple every day, right? And about 3,000, so 10 per day, that made it to the live experimentation state of click evaluations. And then at the end of the funnel, 500 something launches for the day. So it's still like roughly 2 improvements a day that we then usually bundle on a weekly basis into a new release, and then that gets pushed out. And since you don't have to download our software or take a CD or DVD that says, oh, Google 10.3.5 point something, we just do it for you at the back end. You don't even notice it maybe, right? But it's a constantly improving our system. And it's also a nice way of working because it's very bottoms up, right? Like I have an idea, people could say, well, okay, try it out, right? And then it's a limited time investment. Doesn't work, okay, too bad, right? Works, great, right? So it's also easy to parallelize the work within the group of a few hundreds or even thousands of engineers, right? You have a clear experimental, empirical framework that you use for evaluation, and everyone knows kind of the rules of the game, and then you have smart people who try to come up with ideas and make them happen. So that's basically something I wanted to say about search and some of the things we're doing in search. Now let me move on to the next topic that is actually related, which is Google as in Google Scale or Google Scale computing. So if you look at it, we already talked about some of these things. Search queries, 1 billion per day. That means about 10,000 per second. We have large databases that contain up to 70 petabyte of data. Okay, so think of a typical hard disk has about a terabyte capacity, so that is 70,000 disks working together as one big spreadsheet. I will explain how this works later. With about 10 million operations per second being performed on that big spreadsheet, if you like. If you look at storage, we're approaching the zeta range of storage that we have on disk and all the other storage mediums that we have. And the network part for some reason is kind of hidden here, but we are currently about 10 to the 20 bytes per year of network traffic, and we are approaching about 21, which would amount to about 32 kilobits per second for 1 billion people. And things like YouTube and so on and so forth contribute a lot to that. So the starting point, 1998, Stanford, a couple of computers, a bit of Lego, the famous Lego design. That was basically how it got started. And then it evolved. It still looked kind of weird, right? It's not like the hardware you would buy in a nice and shiny hardware store, but you can see, everything kind of self-made, assembled together. And that is really a philosophy that Google has followed over the years. We want to optimize the performance we're getting for the dollars. Okay, so that basically means we're not going to purchase high-performance servers. We're going to buy lots and lots of cheap commodity component hardware. PC class motherboard, low-end storage, networking. We run, of course, Linux on top of that because we don't want to have to build our own operating system. There's a great one out there. Let's use that. Our workload is usually easily parallelized. If we have 1 billion queries per day, each query basically gets processed independently. That makes certain things just easier. Of course, what that means is that we will get failures. Memory will fail. A PC fails. Think about, you have one PC at home, maybe every year or so, you have trouble with it. You have 1,000, you already have 3 problems a day. You have 1 million, you have 3,000 problems per day. So, it's kind of a headache. And then, of course, there's networking failures. There's disks die. All kinds of bad things happen. And basically, the way we had to compensate for that is on the software level. We gain reliability, and I'll point that out with examples later, on the software level where we design the system in a way that it can tolerate all these failures, right? And at the end of the day, if you want to build a global computational platform or a global computer like we have at Google, it really matters that you can do it kind of economically, and I come back to the numbers later. But this is basically how the architecture roughly looks like. You have servers, they have multiple cores or CPUs. The number of CPUs, of course, keeps increasing every year. These things are stacked in racks. Basically, the height of the rack is limited by the size of the typical human so that you can put things in and get things out. 40 to 80, they are connected through an Ethernet switch, and then they're put pretty dense in so-called clusters that are connected through a cluster switch. That creates already, if when I went to university and studied computer science in Bonn, right, we had like local DRAM and maybe one level of caching happening on the machine, right? Now you get a computer that's a very different beast. If you look at like the overall computing machinery that you have, yeah, there seems to be an interesting effect with the laser pointer, which I don't quite understand. It's basically, you really have a memory hierarchy, right, where you have very fast access to the memory on your machine, right, on one specific machine, but then as you have to access things that are in the same rack, things slow down. The whole access times will become larger, right, usually by at least an order of magnitude. And then if you connect things within the same cluster and in different racks, things slow down again, right? So depending on what you want to do, right, it's very important to understand how you lay out your computation in a physical sense, right? What needs to be on the same computer? What needs to be in the same rack? When are you still in the same cluster? When are you in the same data center? And what happens across data centers, which of course is very bad because, you know, the speed of light is only what it is. And unfortunately, the speed of light is sometimes not fast enough for Google. It's, yeah, no, I mean, if you think about it, right, 200 milliseconds, right, that is not a lot of time. And if the speed of light takes up like half of that because you travel halfway around the globe, then that's just bad. So anyway, that's why we need these data centers, and we need lots of them, and we need them all around the world. You can see here speed of light 3,000 kilometers is 10 milliseconds. So that's already like a lot of time that gets wasted that we need to get like through other ways of accelerating the processing of queries. So we don't like to do that. It's a multi-billion-dollar investment. In 2008 alone, we invested more than $2 billion into our hardware. So we love our hardware. And well, over the time, it's probably, you know, don't cite me on it, but it's probably north of $10 billion that we've invested into that compute machinery, okay? So, I mean, you could think that maybe 10, 20 years from now, maybe Google is not known to be a search engine company, but maybe what we're known for is a company that has built a computer at that scale for that price efficiency that we have, right? And actually, a lot of our resources go into that, and there's a very few companies around the world that can do something at a similar scale. So yeah, and you can see here, by the way, this is a data center. I think it's in Oregon, if I'm not mistaken. Yeah, Oregon. This is Washington. And you can see like tiny cars that are like a little, you know, pixel size. So these things are pretty large, right? These data centers. And of course, they consume a lot of energy. So of course, you've heard, and we've tried to also promote that image, of course, in the public. And it is true that we care a lot about energy efficiency. For instance, about half of the energy that we need for data centers goes into cooling, right? So we worked a lot on better cooling strategies using evaporation cooling, using recycled water. And today it takes about a search query, that's an interesting number, requires about 1 joule of energy. Or if you think about carbon dioxide emission, it's about 0.2 gram. Not that I'm an expert here, but these are just the numbers that we publish. And that would amount to car driving of 2 meters. So unless you're not obsessively using Google as a search engine, I think it's pretty okay, right? But because, you know, sometimes people get worried, oh, you know, I do all this search, and doesn't it require a lot of energy? It does, but I think it is small compared to other things like driving cars. What we have then in reality is not so much a data center, but it's really a warehouse scale computer. Because, you know, a data center is usually a facility. You can rent a bunch of computers in there, and then you run your software on these machines. Here it is much more of a centralized, centrally managed pool of resources, much more homogeneous hardware and system software, and everything is integrated, you know, into the design of the facility and the computing machinery. So I think we pioneered a lot of that work of how to go from a data center to a real warehouse scale computer with millions of cores and compute units working together. Okay, so this is kind of the hardware, but as I told you, the hardware is only part of it. So really, on top of that, we need really good software. And since the hardware is faulty because it is commodity hardware. We need really good fault-tolerant software. So the next view on Google, I call Google as a mindset and engineering principle, and I want to tell you a little bit about systems infrastructure. So the first question would be, what do you do on a computer, right? It is storing files and things like that, right? You have your memory stick, there's a file on it, you copy it over. How do you store a large file in a machine like that, right? In that data center, right? So a large file that doesn't fit on one disk, but maybe requires 10,000 disks to be stored, right? So if you want to do that, you need a file system. And so there were some requirements and design principles here that we've been using in building our own file system at Google. That was one of the first things that were built at Google. One is the reliability aspect. The hardware is not reliable, so how can we make the file system be reliable on top of an unreliable hardware? We have pretty big files, so we'd like to be able to store them. We have typical operations that we perform, like append operations, and we want them to be really fast. We often don't need random access to the files. For instance, if it's a log, then we could just add to it. And we also don't need strong consistency. For instance, if things get appended, sometimes doesn't matter in which order they get appended, unless it just needs to be, we need to be sure that ultimately everything gets appended at some point in some order. And we need a very high bandwidth usually for high read-write speeds. So this is basically then the high-level design of the Google file system and of course other file systems, distributed file systems that are out there. If you're a client and you want to, let me say first, what we do is we take, let's say, a huge file that could be, let's say, a petabyte large, and we break it into chunks. Each chunk could be something like 64 megabytes or something of that order. So little pieces, right, that we split up the large file, and these things get stored on servers, so-called chunk servers. And you can see that the same chunks, indicated by the color here, might be replicated multiple times. So the data is not just on one computer, but it is on multiple computers, right? Who knows what is where? That is the so-called master, the GFS master up there. The GFS master memorizes and remembers and manages what goes where. Okay, I did spend that chunk, I did store it here, and the other chunk is here, and there's also a replica there. That master knows who manages the metadata. And then when we have a client system that wants to access a particular file, it talks to the master. The master provides all the pointers, so to speak, to the different pieces that need to be stringed together to then result in the file, right? So if I want to read it sequentially, it would define like an order of the chunks with like the respective chunk server where I can get it from. And then the data transfer can happen directly between the chunk server and the client, and it doesn't have to go through the master, which would be a bottleneck, right? So these are some design principles that get used here. Now, what it basically also means is imagine that, for instance, that server would go down, right? And the master would realize, hey, server number 2 is not responding. It would look up in a table, okay, we have chunk number 1, 3, and 5 stored on that server. I start a new machine now, right? Because I assume this machine is kind of dead or for now not usable. I find where there are replicas of these chunks and copy these replicas over to this new machine, right? So if I have enough replicas around, like a few machines can go down, right, every minute or so, I'm still able to keep the system up and I have no data loss, right? Of course, it's a game with probability, right? And there can, of course, always be situations where, let's say, everything goes down. But we achieve very high reliability, and we had like very, very, very few data losses over the years. So we have about, at Google, 200 such clusters that serve as a big file system. Largest cluster has about 5,000 machines, 5 petabyte disk usage, and about 10,000 other services using that space. So that's pretty large. And then you want to go a step further and actually not just store files, but you want something like a spreadsheet or a table, right? And this is a system that we call Bigtable that basically offers that abstraction. Like a typical use at Google is that you have a URL, right? And you've crawled some information that you want to store somewhere. So maybe you have the content here, maybe you have some images here, maybe you have some metadata information. And you also want like versioning over time. So maybe you've crawled the content at one timestamp and another one. And you would like to keep all of that information like in one really, really large table. The same principle is applied here, divide and conquer. You split the table along the row dimension into smaller tables that are then called tablets. And these tablets are then distributed over multiple machines. They are again replicated if necessary. And the individual data for the little tablets is then stored as a file in the Google file system. And you do similar tricks like you've seen with the Google file system to manage such a large big table. And then there's like, you know, many improvements over the years that have been made here. Certain things can be in memory, so you can access them fast. There's locality groups where if you have to access certain parts of data, you can just group these columns together. There are things like Bloom filters that are used to filter out, like if you want to know whether a certain URL, for instance, exists in the table, that allows you to get an answer faster of whether it is even in the table without having to search through the table. And like lots of other things, right? These things internally within Google, we have usually the way it works organizationally is we have teams that develop these systems and maintain them. And then other teams can just use them internally as service software, right? And so, oops, that was not a good idea. If I have a particular service, right, that I want to run, let's say I'm the news team and I have like a large table that I want to store, then basically I can just put my data into such a table and like there's another team that will basically take care of it and make sure that everything runs. Okay, so again, pretty big tables here and like, again, thousands of disks put together into a big spreadsheet. Okay, now it's time for a break and I'm not sure why this font is behaving so weirdly. But so I walked you through a lot of technical details and we need to take a break. Not really, please stay, but you know, Google is also a paradise for computer scientists. And how does a paradise for computer scientists look like? Well, you know, you just, since we spend a lot of time at work, as probably a lot of you do here too, we would like to make sure that people can relax and then come back refreshed. So this is actually in Google Zurich, a bunch of aquariums, and then you have these comfortable bath tubes filled with something foamy. And you know, you could just relax, or it's also very good after transatlantic flight. Of course, what is more, I would say, a dream for a lot of people working at Google is to work in small teams in front of the whiteboard. Okay, so if you would come to the Zurich office, there's like whiteboard space everywhere, right? And there's people sitting there and discussing, and you know, that's just kind of what you see there. What we also have, and I think that makes also Google very attractive, but it's also very good for the company, obviously, is what we call 20% time. Some of you might have heard this. And it sounds really good, and it is actually really good, which is that 20% of your time or my time, if we work at Google, we can spend on things that we are passionate about, things that we would like to do, and we can do it without manager approval. So I'm a manager, right? It basically means like the developers that work for me, like 1 day a week, they could just go off and do some stuff. Whether I believe in it or not, doesn't matter, right? I can tell them, well, you know, this is really, I don't think so, but they would say, hey, it's my 20% time. And I say, okay, give it a try, right? And often, right, the decision makers in a company are not always the best people to judge every idea, right? It's very good if engineers can say, you know what, it's a great manager, but, you know, often enough he might actually be wrong, so let me try it, right? And so they can start things in 20% time. They can also work together. You can kind of group it, let's say, make it a week, a month, work with a bunch of other folks, and then get something done. So that's actually very satisfying, and it also helps. So actually, I talked to a colleague at a bank once, and he said, hey, this 20% idea, it's really great, because in my bank, people spend 20% of their time complaining that they cannot do anything about how things are, right? So why not give people 20% to do things, and they cannot complain? There's also, like, one principle at Google is team empowerment. Is basically we have teams which are typically 4, 5, 6, 7, up to maybe 10 people. So relatively small groups of people working together. And they are empowered in many ways. They basically can set forward the goals for the next quarter. We usually have a quarterly rhythm, and they can say, we really think we would like to improve our product or whatever we're responsible for, right? Our image search system, we would like to do this and this and this. And then it gets, of course, discussed and ultimately approved by management, but the team is very proactive, right? It's not like top-down, someone at the top says, oh, we need to do something about X, it percolates down, and then at the end, every team knows what they need to do. It's much more a bottom-up process where, with some guidance from above, obviously, in terms of, business requirements and so on and so forth. So it's actually a lot of fun to work at Google, but in order to pay for that, we also need to make money, and basically the way we make money is mainly, as you might know, through advertising, right? And we also engaged in commerce and electronic commerce, and I'd like to just very briefly touch on that. So AdWords, right? So these funny links with the little yellowish background and these things over there, they make us roughly $20 billion per year worldwide, okay? So it's a pretty good idea to have, right? To show ads there, and people don't click on it much, but still, right? We have 1 billion plus searches per day, so it's basically, a nickel here and there that adds up to something quite substantial. And but you should realize that also it's not just showing ads, but what we're doing here is we're running a second prize auction. So advertisers put bids on keywords. We run an auction that combines the bids with a prediction of a click-through, because that's when we get paid, right? Assuming that if someone is willing to pay a lot, but users never click on it because they don't think it's relevant, then that's not good. The ideal case would be something where we think a lot of users will click on it, and also the advertiser is willing to pay a good price for it. So anyway, this runs, right? Every search result, it's not only that we're finding the search results for the search query, but we also have to do these things. And I have to say, like in the back, right? This is probably, as far as I know, the largest machine learning system in the world, right? Like it just processes all the information all the time, because what it mainly does is actually predicting the click-through rate of an ad that we show for a query, right? Because that's what we want to know, right? If we maximize that, we maximize revenue, and we also maximize, we think, the relevance for the user, because typically users only click on things if there is something there, right? And it is interesting, if you think about it, right? Like you're an engineer, you have an idea, you improve the ads targeting system in a way that it increases our revenues by 1%. It makes up for your salary for a couple of lives. So, but then of course not everyone works in ads, so these guys always have to make a little bit more so that the rest of us can enjoy the aquarium and start discussing and doing 20% time, right? But it is like an interesting business, not just the advertising system, really everything, right? You do something in engineering. At Google's scale, it really pays off to do an excellent job and not just kind of an okay job, right? If you do things at like 3 orders of magnitude lower, you could say, oh, well, that solution is good enough. Why spend another quarter improving it? Here, it really pays off to do something out of the extraordinary to really improve things. So that is search ads. There's also AdSense, where we actually share revenue with so-called publishers, where we show ads on websites. We pay them roughly $5 billion a year. So that is also a lot of money that goes into the internet and people who provide content on the internet. And we have a reach of about like 3/4 of the global population through AdSense. So it's very likely that all of you have run across AdSense ads. Now, I'm not saying that they're always great, and I'm not saying that I love them, but it is a fact, and it's another way for us to monetize and actually create a business. So the idea is basically you have a web page. We try to understand what the web page is about and how that relates to ads that we could be showing, and whether we can match certain things that would go well with the content, in the sense that the user that is looking at the page might also be interested in that ad. And that's basically what we do. If you think about the volume of requests that we have to serve here, if you think web search is mind-boggling, this is even more mind-boggling, because every page that gets shown, right, when the HTML, right, is sent over, there's a piece that now Google needs to fill in, right? So you go to whatever, some CNN page, a part of the page is now rendered by Google. We have to put the ads, right? So a lot of page impressions on the web, we have to do some actual work in producing the ads for it. And as I said, you don't just want to put any ads, you want to put good ads that users like so that you really create revenue with it. So it's, again, a huge system, a lot of non-trivial engineering work. Worldwide, we have about 1 million AdWords advertisers and about the same number of AdSense publishers. And also, like, if you look at the total economic activity that is generated by Google, it's actually in the tens of billions. So that is not just our revenue, but also through partners and so on and so forth. I'd like to talk now a little bit about commerce, which is an area that I'm in, just so that you see some of the new things that we're currently tackling. So one thing is that web search often relates to purchasing things online. Okay, so shopping, you would like to know, I would like to buy this camera, where can I really get the best price for it? Or maybe you don't even know what camera to buy or what hard disk to buy, and you would like to do research on it. Google Product Search is doing that for you. That has been around for many years. It's the #1 price comparison site in the US. But what we're currently actually looking into is what we call local shopping and a connection between online world and stores. So we are currently acquiring in-store availability data. All right? In the US, we started with large chains. What does that mean? Is like we create an index for each store, starting with these chains, of what is in that store now, like real-time inventory. Can I go to that store and pick up that product, and at what price, and how many, TVs or what are still in that store, right? That's a huge effort that we're currently working on. And we'd like to bring like the online world and the store world closer together, and also drive or encourage people to actually go to stores, to local stores, instead of purchasing everything online. We also build mobile applications that support that. Google Shopper is one that does that, but let me just move on here. Some of the more speculative things that we're currently working on, you might have heard this, I think it was last week, the Google Wallet. Okay, you use your Android smartphone and all your credit cards, all your loyalty cards, everything's on that mobile wallet, and you go into a store and you just pay with your Android. So you don't have to carry all these things around. We're also looking into Google Offers, which is, like Groupon and other type of offers, special deals that people get. So this wallet, I think, is in my eyes, is really something that will revolutionize. Whether it will be the Google Wallet or, another wallet, I don't know. But I think for sure, in 10 years or so down the line, it will revolutionize the way we organize our payments through these mobile smartphones. Okay, so much about ads and commerce. I have like a few more things here, not that much about research. We do a lot of research at Google, but I didn't want to really give a research talk here, but more of like a systems building, engineering type of talk. So these are some areas, right, that probably whatever area you work on, it's likely, at least if it has something to do with computing and maybe electrical engineering, that we are interested in it. But some things I would like to point out, just a random sample here, is, for instance, machine translation. Okay, so I think at Google, we built one of the largest production machine translation systems, right? It's like, nothing else really compares to it because of the way it's basically integrated in web search, right? I don't know whether you're a user of it, but if you're like me, non-English speaker, right? There's lots of pages you run across that maybe you would like to get translated from various languages. So it's integrated into Chrome toolbar. We use it for YouTube. You can get your Gmail, your email translated, or your online documents. It has like a lot of use, and it is like one of the best systems quality-wise that is out there. And again, what makes that possible is that we process large amounts of data. So because this is statistical machine translation, And by processing a lot of data that we find on the web, basically parallel corpora of pages that are available in multiple languages, we use that to train the system and to build this machine translation system. There's much more. We invest in automatic speech recognition and like many other things, right, that we think are critical. Yeah, and then in the end, I just wanted to basically highlight another project, because every now and then we also just do things that we feel passionate about, even if it is maybe not changing the world. But one example is the arts project, which was largely done on 20% time, right? And the idea was that some engineers at Google said, well, look, you know, we have all these fantastic imaging technology. We have Street View, right, where we can process lots of data. We have software that can basically stitch images together at a large scale. And, you know, we have all these things. What can we do other interesting things with it? And out of this came the idea of the Google Arts project, where we worked with 17 museums, the ones that are listed there. And we created a new online experience where at the same time you can walk through in a Street View like navigation setting through the museum without being there. Okay, you can, you know, walk through the halls and halls of the museum, and you can also look at images. And we had some images that we actually scanned at very high resolution. So here's an example. I could show it live here, but it would take too much time, so I just skipped through this. I think this is National Gallery in London, and there were, like, from each museum, we had one image that we digitized at a giga-plus level resolution. So that basically, I don't know whether you've seen that, but that basically means, like, compared to a usual photo, you would have 10 times 10 higher resolution, so it corresponds to roughly 100 or so regular photos. And then you can really zoom in here if you look at the globe, right, down to the level where you can actually see the strokes and the brush, right? And probably, I mean, even if you go with a magnifying glass in the museum, probably you couldn't get close enough to the painting to actually see these details, right? So that's a nice example. Lots of challenges technical challenges that have to be overcome if you want to do that. A lot of which we had to deal with in Street View, but there's also other additional challenges that come with indoor environments, like very, you know, high variability in lighting and so on and so forth. And at the very end, I will just show you a video while I take a glass of water here about this project. Yes, I know the problem. No, don't give up here. We have a backup at YouTube. It's good we bought that company. And there's also audio, if we can hear the audio. Oh yeah, we can hear the audio. So this is a video about the makings of the museum project. So this is the street view inside of the museum. And finally, I should say some good press for Street View, where the press has not always been so positive. Yeah. So that's nice to work at a company where you could just do that every now and then. And then I'm basically through with my presentation, and I'm awaiting your questions. Thank you.
Well, I think we'd all agree that was a great lecture. I'd say it was a brilliant lecture. But then, what would you expect? Because probably all the employees at Google are brilliant, all 25,000 of them. And I think what is so brilliant as a user is that you can't see all this. I mean, you don't want to see it. You want to just be able to use Google and not to think about how it's all done. And the miracle is that that's what happens. If you want to translate something from Haitian and Creole into English, you don't have to think about what the software is doing. You just get on with it. I find, I'm responsible for a lot of the searches, not the whole 2 billion.
Thank you. We appreciate your business.
Quite honestly, I can't imagine what we did before Google was invented. I mean, you don't go to the library as frequently as you did in the past, because, as this is saying, you can look it up, whether it's your symptoms of a fell disease that you think you're about to get, or some abstruse query about what's happening in Rwanda. I think Google Alerts is a fantastic benefit for anybody who's doing a regular amount of research on a large number of subjects. You just signal that you want the alerts on Yemen or whatever it may be, and they come up regularly without you having to think about how that's done. I'm so glad we had you, Professor Hofmann, to lecture us today, and I think it is everybody would agree that it's one of the most brilliant lectures that we've had in all the 37 that have been delivered in the engineering laboratories. So I'd like to propose a very hearty vote of thanks to Thomas Hofmann.